Welcome to my series on difference equations. This is a six-part video series. In the first lesson, I'm going to talk about foundations, and we'll look at things like recurrence relations and different classifications of these recurrence relations. This is section 4 of my book, Mathematical Vignettes. I'll give you a link to the electronic version, which is free to download. This is a quick summary of the series. So this is the first lesson, as I mentioned, on foundations and classification. Then we have what are called first-order linear equations. These are a little bit simpler. Then there's higher-order linear equations, non-homogeneous equations, and then nonlinear equations, and chaos. In terms of prerequisites, it's not too much. Arithmetic and algebra, sequences and infinite series, the idea of a limit from calculus, a little bit of trigonometry in one lesson only. You've probably seen sequences before in different problems, quizzes. So let's start off with a simple one. A recurrence relation or a difference equation defines a sequence recursively. The rule says how each term follows from the ones before it. Given a starting term or terms, everything else is determined. So we have here a definition. We're given the first term, and then we're told the difference between terms is 3. So the difference between 0 and term 1 is 3. That means it's 7. And then the difference between this and the next one would also be 3, right? It's constant difference. So that would be 10. Then 13, and then 16. So you've probably seen something at this level, even in grade school, and you're asked, well, what's the next one? And you just kind of notice there's 3, 3, 3, and 3. And so the next one would be 19, right? You're adding just 3 each time. So this is called an arithmetic sequence. The difference between consecutive terms is constant. Why do we use the phrase difference equation? It's because a lot of these sequences can be written as a difference, as we saw in our first example. So this difference gives us the rule for computing additional terms. It's also related to differential equations. It's sort of the discrete analog. So your dy dt in calculus is similar to the recurrence relationship that we've seen. So continuous on the left and discrete on the right. The two subjects run in parallel. We're going to just focus on the discrete side here. There's 4 different classifications or methods of classifying a difference equation. One is the order. How many earlier terms does the rule need? Then there's linearity. Do the sequence terms appear only to the first power? So the example we just saw, that was first order and it was linear. Homogeneous. Is there a standalone forcing term? We'll have to see some examples to understand what this one means. Then autonomy, are all the coefficients constant? So we'll continue with some examples of these just to reinforce the definitions. The order of a difference equation is the number of previous terms you need to know in order to compute the next one. If you only need the previous term, it's first order. So we have an example of this here. You're given x0 is 2, then x1 would be 5 times 2, and then x2 would be 5 times that, so it would be 50, then 5 times that. So you only need to know the previous term. So it's first order, and this happens to be a geometric sequence. because you're multiplying now rather than just adding. I have a couple more examples. This is order 3. You notice you're given 3 initial terms, and then to go beyond that, you need to add the last 3 terms in order to get the next one. So you need to add 1 plus 1 plus 1 to get 3, and then 1 plus 1 plus 3 to get 5, then 1, 3, and 5 added to get 9. So this is called the Tribonacci sequence, and it's of order 3 because you need to know the previous 3 terms to get the next one. Then you have, this one's a little bit odd because you have a skip here. You need to look back 2 terms in order to compute the next term. So in order to get this one here, you need to look back to the first term and multiply by 3. Then to get this, you need to look back to this 2 terms before, multiply by 3, and then to get this one, you have to multiply 3 times this. To get this 9, you need to multiply 3 times this. I'll just do one more. To get this one here, you need to go back 2 and multiply 3 to get 27. So this is a second order. So you can look at it this way. You can look at it as x n plus 1 equals 0 times x sub n plus 3 times x sub n minus 1. So this is order 2. Because you have to look back 2. Even though you don't have to look back 1, the order is really based on the maximum number of terms you need to look back. Linearity, the next classification. A difference equation is linear if the terms representing the sequence appear only in the first power. So this is not linear. We have an x sub n squared here in order to find the next term. So this is not linear. Then this is linear. The coefficient change with n, but the sequence terms are still to the first power. So linearity is based on the terms in the sequence. Neither one of these is raised to a power higher than 1. And then these n's, it's 3n here. That doesn't change the fact that this is linear. It's based on the definition of the linearity. I have listed here a general linear difference equation of order k. If you notice here, it starts at n and goes to n plus k. So there's k plus 1 terms, which means you need k consecutive values in order to determine the rest of the sequence. We can also use this equation to define homogeneous and autonomous. If this b of n is 0, then it's homogeneous. And bn is just whatever terms are not multiplied times the nx. If you just take those to one side, and if they're not 0, then you're not homogeneous. And then these coefficients, a1, a2, up to ak, if they're not constant, then you're not autonomous. And if they're constant, if they're all constant, then you're autonomous. In fact, if any one of these is not a constant, then you would be classified as non-autonomous. And one other point is you don't need to have the k consecutive values don't need to be the first k. You could have like you go out 10 terms, for example, and then give k consecutive, and then you can work backwards and forward to get the rest of the sequence. So as we saw in the previous slide, the b of n needs to be 0 for the difference equation to be classified as homogeneous. If the right-hand side is 0, the equation is homogeneous. Bn is the forcing term. That's the terminology used. It stands alone, multiplying no member of the sequence. Homogeneous equations are the ones we can solve outright. A nonlinear Bn is handled in part 5 or lesson 5 by solving the homogeneous version first and then patching in a correction. So I have some examples here. We can move this 5x sub n to the left, and we get a 0. So this is homogeneous, and we can move all these three terms to the left by subtracting them, and then we have a 0 here. We can move nx sub n to the left, but then you're still left with this 3n. It's not multiplied times any member of the sequence, so this would make the difference equation non-homogeneous. Same problem here, you have a 3 on the right, and all the other terms involving the x are on the left, so this is non-homogeneous also. Autonomous, if every coefficient is constant, the equation is autonomous. Formally, all the a sub I of n and b of n are constant. Constant coefficients mean the rule is the same at every step. Coefficients that vary with n make the equation non-autonomous, and the closed form gets harder. We'll see that as we try to solve some of those later. There is no standard noun for this property, so we simply say the equation is or is not autonomous. So which is autonomous, which is not? So we have some examples. This is autonomous. It's also homogeneous. This is autonomous. We have constants times our x terms, but it's non-homogeneous. Then this, which we've seen several times in different variations, this is not autonomous because of the n here and also the 3n. It's also non-homogeneous. So we can also have nonlinear equations. We're not going to deal with these very much, but I'll show you an example here. So it's nonlinear because this term is cubed. It's non-homogeneous because you can, even though you can take these three terms involving an x to the left, you still have this 7n. So it's non-homogeneous. It's order 3 because you need to know the value of the sequence for 3 previous terms. And it's also non-autonomous because of the 7 to the n, and also because of the n squared here. Okay, so this is a nasty one. I'm not sure how to solve this, to be honest, but I mainly put it here as just to illustrate nonlinear equations, and then you just noting that you can also apply the same classifications in terms of order, homogeneous or not, autonomous or not. Some takeaways from lesson 1. A difference equation defines a sequence recursively. The goal is to get a closed form so we can just read off whatever the 100th term without having to compute all the terms in between. And we'll get to that later in future lessons. Order is how far back the rule reaches and how many initial conditions you need. Linear means the sequence terms appear to the first power. Homogeneous means no standalone forcing term. Autonomous means every coefficient is a constant. So coming up in lesson 2, and I sometimes use the word part and lesson interchangeably, the general first order linear equation is covered, and we derive a closed form solution. Why that formula is unwieldy and why we derive it anyway. The geometric sequence has its simple special case. So we'll talk about that. We already saw an example of a geometric sequence. Compound interest is an example of a geometric sequence, so we'll work an example of that. And we'll go from there. So the sequences get a little more complex as we get into future lessons.